Welcome to ODEs Lesson 20, Matrices. We will be solving systems of linear equations using matrices and Gaussian elimination. We're also, besides talking about matrices and Gaussian elimination, we will talk about another method called Gauss Jordan elimination. We could start with a system of algebraic linear equations, such as these here, and we will write that in terms of a matrix called the augmented matrix. Then we can find the reduced row echelon form of that matrix and use that to find all solutions to the system of equations. What will we learn in this lesson? We will learn how to think about systems of algebraic linear equations in terms of matrices and numbers. In this lesson, we are talking about algebraic equations. We'll also see how to transform these matrices into row equivalent matrices so that we can easily write down the solution set to the system of equations, linear equations. We will also be able to determine if such a system of algebraic linear equations has no solution, or exactly one solution, or an infinite number of solutions. So why learn to do this? Why represent a system of algebraic linear equations in terms of matrices and use matrices to solve them? Well, there are many reasons. Here are a few. In solving an initial value problem, an ordinary differential equation plus initial conditions, we often must solve a system of linear algebraic equations. A system of first-order linear ordinary differential equations is often handled through matrix methods. Also, outside the realm of ordinary differential equations, systems of equations are often used in numerical analysis and other branches of math, physics, and engineering. And besides that, if you're in math or one of the sciences that requires computation, courses in linear algebra often cover, almost always cover, topics concerning linear transformations and how to represent them by matrices. Let's look at an example involving an initial value problem that has a system of linear equations resulting. Let's look at the following fourth order ordinary differential equation. Fourth derivative of y with respect to x plus 2 times the third derivative of y minus 11 times the second derivative of y minus 12 times the first derivative of y plus 36y equals 0. If we write out the characteristic equation, it's going to be what? R to the fourth plus 2r cubed minus 11r squared minus 12r plus 36 equals 0 on the other side. That factors into r minus 2 quantity squared times r plus 3 quantity squared equals 0. So we have a root r equals 2 of multiplicity 2, algebraic multiplicity 2, and r equals minus 3 also has algebraic multiplicity 2. So what do we get? Y of x, the solution, the general solution to this differential equation, has to look like this. Y of x equals a constant c1 e to the minus 3x plus c sub 2 x e to the minus 3x plus c sub 3 e to the 2x plus c sub 4 x e to the 2x. So now let's look at the following initial value problem. First we have that differential equation from up here, and we have these initial conditions. Y of 0 is 7, y prime of 0 is 9, y double prime of 0 is minus 2, third derivative of y at 0 is 5. Well, what can we do with this? Since we know what y of x is, we have that right here, we can calculate these derivatives that we see over here and substitute 0 in. And when you do that, y of 0 turns out to be c1 plus c3, and according to this initial condition, that has to be 7. Y prime of 0 turns out to be this stuff, and by its initial condition, it has to be 9. The second derivative of y at 0 has to be minus 2. The third derivative of y at 0, this stuff has to be 5. So basically, we left out a little bit of algebra here. We would have to calculate each of these derivatives and then substitute in 0. And once we do that, we just get this stuff here. And so, in order for this thing to be a solution to this initial value problem, we have to find the C1, C2, C3, C4 that satisfy these equations right here, which I have just copied down here. So what we have here are 4 equations in the 4 unknowns, C sub 1, C sub 2, C sub 3, and C sub 4. A system of algebraic linear equations is composed of one or more algebraic equations, each of degree 1. Here, first are some examples of linear equations. 2 times x plus 3 times y equals 39. This is a linear equation in the two variables x and y, or we could say the two unknowns values x and y. This one, 4x minus y plus 3z equals 18, is also linear. We could use subscripted variables like 4 times the variable x sub 1 minus the variable x sub 2 plus 3 times the variable x sub 3 equals 18. If we look at this last equation, in some way it's equivalent to the second equation that we have up here. Instead of using x, y, and z, we used x sub 1, x sub 2, and x sub 3. Why would we want to use subscripted variables? Well, there are, about 26 letters in the alphabet. X, Y, and Z are 3 of those. If we just use letters, we'd be restricted to, I guess, about 26 variables. We might have problems with 100 variables or 1,000 variables or more. So subscripted variables in general are the way to go. Here are a couple equations that are not linear. 2x squared plus 3y equals 39. Notice that we have an x squared term here, so that does not have degree 1. This term does not have degree 1. And 5 times x times y equals 2. Why is this not linear? You might say, well, don't we have x to the first power and y to the first power? Yes, but to be linear, it has to be something like a constant times a variable to the first power in each case. Here we have two variables, x to the first power times y to the first power. This is actually a quadratic equation. We can get that it's quadratic, degree 2, by adding the powers of the x variable and y variable together, since those two variables are multiplied together. So in general, a linear equation in the variables x sub 1, x sub 2 through x sub n can be written this way: a constant a sub 1 times x sub 1 plus a constant a sub 2 times x sub 2 plus on and on to the final term plus a sub n x sub n equals a constant b. This is going to be the general form of a linear equation in n variables, and a system of linear equations would consist of one or more of these linear equations. So, let's look at a system of two linear equations and two unknowns. We're going to be considering the general form of these equations. Here we have two equations, and the first equation involves the variables x sub 1 and x sub 2, and the second equation also involves x sub 1 and x sub 2. The a's and the b's are constants. So if we have two linear equations and two unknowns, in general we could write them this way for some choices of these constants. Here are some examples. We could have 2x sub 1 minus x sub 2 equals 5, x sub 1 plus x sub 2 equals 4. This is a system of two equations and two unknowns. We could also have 2x minus y equals 5, x plus y equals 4. These are two linear equations in the variables x and y. We could also have a system 2 times a minus b equals 5, a plus b equals 4. This is a system of linear equations in the variables a and b. We mentioned before that the solution set to a system of linear equations can be empty, or have exactly one solution, or have an infinite number of solutions. Let's look at examples of each of these. How could the solution set be empty? Let's look at these two equations. 2x sub 1 plus 3x sub 2 equals 1, 4x sub 1 plus 6x sub 2 equals 5. Notice that if I multiplied this first equation on both sides by a factor of 2, we would have 4x sub 1 plus 6x sub 2, which is the same thing I have down here, equals 2, not 5. So it's impossible to find values of x sub 1 and x sub 2 that make both of these equations true. So there is no solution to this system of equations. Suppose we look at this example. 2x1 plus 3x sub 2 equals 1, x sub 1 minus x sub 2 equals 5. If we think of one of the axes as being the x1 axis and the other as being the x2 axis, and graph these two equations, this equation would have a graph that's a line, this equation would have a graph that's a line, and these two lines intersect at a point, and the coordinates of this intersection point would be on both lines, and thus would satisfy both of these equations. Exactly one solution, and it's given by the coordinates of this intersection point. How could we have an infinite number of solutions? Well, suppose we had 2x1 minus 3x2 equals 1, 4x1 minus 6x2 equals 2. Notice this second equation is just twice this first equation. They're basically equivalent equations. This first one has a graph that's a line, given in red here. The second one has a graph that's a line, maybe given in blue, and they're actually the same line. Every point on this line has coordinates that satisfy both of these equations, and thus we have an infinite number of solutions. In this case, it's easy to see that we have an infinite number of solutions for this particularly simple system of equations. If we had, say, 5 equations in 5 unknowns, it would be much more difficult to tell which one of these cases is occurring. One of the things that we will do in this lesson is find how we can distinguish these three cases for a particular system of equations. Let's talk about solving a system of equations by elimination of variables. You can find the system of a solution of linear equations by using these operations. 1. Multiplying an equation by a non-zero constant. 2. Swapping two equations. And 3. Adding a multiple of one equation to another equation. By using these three operations on a system of equations, system of linear equations, we can find solutions fairly easily. So let's see an example using elimination of variables. Let's find the solution set to the following system of equations. 2 times x sub 1 plus 3 times x sub 2 equals 1, x sub 1 minus x sub 2 equals 5. If we look at these two equations, it would be nice if we could get rid of this x sub 1 term in the second equation. Why don't we multiply that second equation by 2, so it'll become 2x1 minus 2x sub 2, and together with the first equation we now have this resulting system. If we subtract the second equation from the first equation, let's see what happens. 2x 2x sub 1 minus 2x sub 1 is 0x sub 1, minus 2x sub 2 minus a plus 3x sub 2 is equal to minus 5x sub 2, and 10 minus 1 is 9. So now we have this system of equations. If we look at this second equation, the x1 term has the coefficient of 0, so this equation really is just minus 5x sub 2 equals 9, and we can solve that equation easily for x sub 2. So minus 5x sub 2 equals 9, so x sub 2 equals minus 9/5. Then we can substitute this value of x sub 2 into, let's say, this first equation and solve for x sub 1. 2x sub 1 plus 3 times minus 9/5 equals 1. Let's change this 1 to 5/5, so we can write that equation this way. And then we have 2x1 minus 27/5 equals 5/5. Let's add 27/5 to both sides, and we end up with 2x sub 1 equals 5/5 plus 27/5, which is 32/5. And then divide both sides of this equation by 2. Dividing this side by 2, we get x sub 1. Dividing this side by 2, we get 16/5. So what we found out is that there is only one solution to this system of equations. X sub 1 has to be 16/5, and x sub 2 equals minus 9/5. So that was fairly easy to solve, and it in any case would have been easy using almost any method we know, because it's only two equations and two unknowns. And in this form, the last form that we had up here, is particularly easy to solve because we had a 0 here. And so one question that we want to answer is, how can we go from this beginning system of equations to an equivalent system down here that has the same solution set in a nice orderly fashion where we know what to do at each stage? We will see that we can solve this type of problem and more complicated problems, more equations, more unknowns, using matrices and Gaussian elimination. Let's talk about matrices. A matrix is a rectangular array of numbers, or it could be a rectangular array of other things. We'll mainly talk about numbers. An m by n matrix is a rectangular array of numbers with m horizontal rows and n vertical columns. And we read this as m by n matrix. Let's let A be the following matrix. If we look at this matrix, it has two horizontal rows, and it has 1, 2, 3 columns. So that makes it a 2 by 3 matrix. We could also say that the size of A is 2 by 3. Suppose I let X be this matrix. Here we have one column, but we have 3 rows. So let's reiterate, 3 rows, 1 column. So that makes X a 3 by 1 matrix. Let's let Y be this matrix. This matrix has 1 row and 3 columns. So Y is a 1 by 3 matrix. This matrix, which consists of just 1 column of entries, is also called a column vector. And this matrix, which just has 1 row of entries, is called a row vector. Let's talk about the matrix associated with a system of linear equations. Actually, we'll look at two matrices that are associated with a system of linear equations. Suppose here are the linear equations. A sub 1, 1, x1 plus a sub 1, 2, x2 plus all the way through a sub 1n, x sub n equals b sub 1. And then the next equation, a sub 2, 1, x sub 1 plus a sub 2, 2, x sub 2 plus all the way through a sub 2n, x sub n equals b sub 2. And the final equation, which will be, let's say, our mth equation, we're looking at m equations and n variables here. The last equation, a sub m1, x1 plus a sub m2, x sub 2 plus all the way through a sub mn times x sub n equals b sub n. All of the a's in these equations with the double subscripts are constants, and these b's are also constants. The variables are x sub 1, x sub 2, all the way through x sub n. So since we have m equations here and we have n variables, this, as I said, is a system of m equations and n variables. First of all, let's just look at the left-hand side of this system of equations. Let's just keep the constant multiples of those variables and throw away the rest. If we do that, we get the coefficient matrix for this system of linear equations. The first row is just a sub 1, 1 through a sub 1n, and then you'll have a sub 2, 1 through a sub 2n, all the way through this last equation, a sub m1 through a sub mn. So this will be an m by n matrix. The size of this matrix A is m by n. Remember that all these a's are just coefficients of the variables that occurred in these equations up here. If I look at a particular element, a sub ij, what does this mean? We'll let it mean that that's the element in the matrix A, that's in the ith row and jth column of that matrix. And as I mentioned perhaps, it's called the ijth element of the matrix A. Well, this coefficient matrix is not enough for us to represent these equations entirely, because we also have these constants on the right-hand side of these equations. The augmented matrix for the system of equations looks like the coefficient matrix that we had here, just copied in this portion right here, augmented or increased by one column. And this column are the values b1, b2 through b sub m that are on the right-hand side of the equations. So this augmented matrix, on the left side of it we have A right here, and on the right side of it we have the column B. So this is the matrix A augmented by B. So the last column of this matrix are just the constants from this right side of the equations. This matrix has all of the information contained in this system of equations. So somehow, to solve this system of equations, we're going to look at this augmented matrix and make certain types of transformations on this augmented matrix to get a simpler set of equations that is equivalent to the one we started with, and one that will be fairly simple to solve. Let's look at an example of matrices associated with a system of linear equations. Let's look at this system of equations. X sub 1 plus 2x sub 2 plus x sub 3 equals 4. Second equation, 3x sub 1 plus 8x sub 2 plus 7x sub 3 equals 20. And the third equation, 2x sub 1 plus 7x sub 2 plus 9x sub 3 equals 23. The coefficient matrix for this system of equations is just this matrix here, 1, 2, 1 in the first row, second row 3, 8, 7, third row 2, 7, 9. we can see that they came from the system right up here by looking at the coefficients. 1, 2, 1, 3, 8, 7, 2, 7, 9. So we have this 3 by 3 matrix. A matrix that has the same number of rows as columns is often called a square matrix. This is an example of a square matrix. Now, for the same system of equations, let's look at the augmented matrix. Well, it's easy to write down. First, we write down the coefficient matrix, which is right here, and then we augment it by the values on the right-hand side of the equations, and that makes this last rightmost fourth column in this augmented matrix for 2023, for 2023. Here's another example from our initial value problem example, the fourth order ordinary differential equation with the initial conditions. We got these equations that C1, C2, C3, C4 had to satisfy. These C's were the coefficients of certain things, and we had to solve these. Looking at this system of equations, we can write down the coefficient matrix and also the augmented matrix for the system. The coefficient matrix is going to be what? We just look at the left-hand side. In this first equation, C1 has a coefficient of 1, C2 has a coefficient of 0, since we don't see it here, C3 has a coefficient of 1, and C4 has a coefficient of 0. So the first row is going to be 1, 0, 1, 0. The coefficient of C1, C2, C3, and C4. From the second equation, the second row of this coefficient matrix is minus 3, 1, 2, 1. The third row is 9, minus 6, 4, 4. And the last row is 27, 27, 8, 12. The augmented matrix looks very similar. This part of the matrix right here is the same as the coefficient matrix. We have, however, an extra column, and this extra column are the numbers that appeared on the right-hand side of this equation. 7, 9, minus 2, and 5, 7, 9, minus 2, and 5. So the augmented matrix is the coefficient augmented by one additional column. So let's talk about elementary row operations that can be performed on a matrix. These are going to be operations that will correspond to a system of equations equivalent to the one that we started with. So let's look at elementary row operations that will get us a new ith row. One is to multiply the ith row, let's say, by a non-zero constant. I can write that as the new row, ith row, r sub I, is a constant times the old row, r sub I. So when we look at this, this is an assignment statement rather than an equation. The value of the right-hand side is evaluated, c times the ith row, and that is stored in the left-hand side as the new ith row. We can also interchange two rows. We can interchange the ith and jth rows. We use a double arrow for this to represent the fact that we're interchanging or swapping two rows. We can also add a multiple of one row to another. We could take the ith row plus a constant times the jth row and store that as the new ith row. So these are the three elementary row operations. Whenever we use elementary row operations on an augmented matrix, the resulting matrix corresponds to an equivalent system of equations. That system has the same solution set as the original system of equations. So, whenever we use a sequence of elementary row operations, one row operation after another on an augmented matrix, the final matrix also corresponds to an equivalent system of equations. So we can do quite a bit of transformations on a matrix using these elementary row operations in order to get it into a matrix where it is very easy to see what the solution set has to be. As an example, let's find the solution set to this system of equations. X sub 1 plus 2x sub 2 plus x sub 3 equals 4. 3x sub 1 plus 8x sub 2 plus 7x sub 3 equals 20. 2x sub 1 plus 7x sub 2 plus 9x sub 3 equals 23. So the first thing we'll do is we'll write out the augmented matrix for this system of equations. And the first row is 1, 2, 1, 4 from this first equation. The second row is 3, 8, 7, 20. And the third row is 2, 7, 9, 23. Those last two rows correspond to these last two equations. Now, the first thing I want to do is to use this first row, and very specifically the 1 in this first row, to get a 0 here instead of a 3. So here's what we'll do. We'll take row 2 minus 3 times row 1, and we'll store that as the new row 2. So let's see. The first element is going to be 3 minus 3 times 1. The second element of row 2 is going to be 8 minus 3 times 2. The third one is 7 minus 3 times 1. And the fourth element is 20 minus 3 times 4. Okay, so let's see. 3 minus 3 is 0. 8 minus 6 is 2. 7 minus 3 is 4. 20 minus 12 is 8. So this matrix is equal to this matrix. So the next thing we'll do is look at this matrix. And I would like to get a 1 here. I can do that by just multiplying row 2 by a half. Row 2 equals a half row 2. So this row 0, 2, 4, 8 becomes 0, 1, 2, 4. Okay, and now I would like to get a 0 here in the third row, and I'll do that by subtracting an appropriate multiple of row 1 from it. So row 3 is going to equal row 3 minus twice row 1. So let's see, 2 minus 2 times 1 is 0. 7 minus 2 times 2 is 3. 9 minus 2 times 1 is 7. 23 minus 8 is 15. So we now have this matrix after this elementary row operation. So now I'd like to get a 0 here using row 2. I can subtract 3 times row 2 from row 3. So row 3 equals row 3 minus 3 times row 2. So what happens is 0 minus 3 times 0 is still 0. 3 minus 3 times 1 is 0. 7 minus 3 times 2 is 1. 15 minus 3 times 4 is 3. So we now have this matrix. This is an especially nice matrix. In the first row, the leftmost non-zero element is a 1. In the second row, the leftmost non-zero element is 1. And in the third row, the leftmost non-zero element is 1. And as you go from top to bottom, from first row to second row to third row, those leading ones are going towards the right. And if you have that satisfied, this matrix, we will say, is in row echelon form. So now we can easily solve our system of equations by back substitution. We'll start with the last equation and work our way up to the first equation. So this last equation is 1 times x sub 3 equals 3. because this is basically 1 times x sub 3 equals 3 here. So x sub 3 equals 3. Then we go to this row, and we have 1 times x sub 2 plus 2 times x sub 3 has to equal 4. And that's what we have here. X sub 2 plus 2x sub 3 equals 4. But we know that x sub 3 is 3. So x sub 2 plus 6 equals 4. So x sub 2 has to equal minus 2. So far we've used the last equation to find x sub 3. We used this next up to find x sub 2. Now we'll go to the top equation corresponding to this row to solve for x sub 1. So this row gives us x sub 1 plus 2x sub 2 plus x sub 3 equals 4. And we know what x sub 2 and x sub 3 are, so substitute them in. X sub 1 plus 2 times minus 2 plus 3 equals 4. And so x sub 1 is going to equal 5. So that tells us that the solution to this system of equations is the following. The column vector x1, x2, x3 has to equal 5 minus 2 and 3. This is the only solution to that system of equations. We saw before that a system of linear equations can have no solutions, or exactly one solution, or an infinite number of solutions. In this case, we have exactly one solution. So here's a fact that we need to know. Elementary row operations on an augmented matrix for a system of equations results in an augmented matrix for an equivalent system of equations. They have the same solution set. The solution sets are identical. Now, we did it by hand. We found an equivalent system of equations by using elementary row operations, but it requires a lot of calculations, and sometimes it can get messy. Calculators and computer software are nice in that many calculators do allow you to store matrices, for instance, an augmented matrix for a system of equations, and to perform elementary row operations. TI-84 calculators are prevalent, and they do have elementary row operations built in. It's in the matrix menu. If you want to multiply row I by a non-zero constant c, you use the command star row, and then parentheses c, the matrix that you're working on, let's call it A, and I for the ith row. Suppose you want to swap rows I and j. There's a built-in function on the TI-84 calculator to do that. Row swap. First the matrix A, and then the indices I and j. Suppose we want to do this third elementary row operation. Row I is going to equal the old row I plus a constant times the old row j. The command in the TI-84 that does that, the built-in function, is star row plus. And then in parentheses, we first have the constant c, then the matrix A that we're operating on, and then j, we're computing c times r, j, row j, and we're storing it in row I. So these are the commands on the TI-84 calculator. You can get to those by using the matrix command, and then you can edit a matrix. You can enter a matrix using a matrix editor, and then you can use these three commands to do elementary row operations. One thing to point out is when you do one of these operations on a matrix A, it does not change the matrix A. The result of that operation will be shown to you, but if you want to store it back in A, you'll have to say something like A equals star row and this sort of stuff. to make sure that you replace the matrix A with the new one that was created using an elementary row operation. Okay, so we're going to first in MATLAB create an augmented matrix for that system of equations. So we'll let A be the matrix, and for a matrix we can use these square brackets, and then the first row 1, 2, 1, 4, and then a semicolon. Then the second row 3, 8, 7, 20, and then a semicolon, and then 2, 7, 9, 23. So notice that in this notation we used a semicolon to separate one row from another, and we used commas to separate elements of a row from each other. So when we had 1, 2, 1, 4 for the first row, we wrote 1, 2, 1, 4, and then semicolon to get to the second row. So at this stage we have our augmented matrix representing that system of linear equations. Now I look at this and I say, well, it'd be nice if I could get 0 here and 0 here to eliminate some x sub 1 terms. And so what I'd like to do is add -3 times the first row to row 2 of this matrix. And to do that, I will say the following. A Okay, try that again. A, and then sub 2 comma colon. That colon is kind of a wild character that represents all the possible values. So this is a notation for the row a sub 2 1, a sub 2 2, a sub 2 3, a sub 2 4. And now we want to let that equal the old second row. So I'm going to type a sub 2 comma colon again, minus 3 dot times, whoops, backspace, times a sub 1 comma colon. Okay, so we take this formula, the second row of A minus 3 times the first row of A, and whatever that is, we store that in this assignment statement as the second row of A. So let's hit enter. And so now it tells us what the matrix A looks like after that. And notice that this second row is different from what it is up here, because 3 minus 3 times 1 is 0, 8 minus 3 times 2 is 2, 7 minus 3 times 1 is 4, 20 minus 3 times 4 is 8. And the first row and the third row were unchanged. So now let's do something similar to that. Let's subtract twice the first row from the third row. And to make the typing quicker, I'm going to use the up arrow to get that last thing that we did. And I'm going to use the left arrow to come over to here, and then a backspace. So I'm going to change that to a sub 3 1 equals a sub 3 1 minus 2 times a sub 1 0. So the third row of A, this new matrix here is now A, is equal to the following stuff. the third row of A minus 2 times the first row of A. When we're talking about multiplying a, let's say, a vector, a row for instance, by a constant, in general we can use 2 dot times to do it. I think 2 times would also work. We might try that a little bit later. Maybe without this dot it'll still work. But in any case, let's see what we get after we execute this command. Okay, so what happened here, we have a new third row, and we got it the following way. 2 minus 2 times 1 is 0. 7 minus 2 times 2 is 3. 9 minus 2 times 1 is 7. 28 minus 2 times 4 is 15. Okay, so now we have a fairly nice matrix. We've eliminated terms involving x sub 1 from the second and third equations. Now, let's do the following. Let's get a 0 here by using this first row. And I can do that by just, well, actually I can't do it quite, can I? Let's do the following instead. Let's multiply this second row by a half so that we get a 1 here. And so how am I going to do that? Well, I want the second row of A, which is A sub 2 comma colon. I want that to equal 1/2 times A sub 2 comma colon. Okay, this time I didn't use dot star for multiplication. I think just a star will work here. Let's see if it does. So I hit enter, and yes, it did. The second row now, instead of being 0, 2, 4, 8, is 0, 1, 2, 4. And now let's get a 0 down here instead of a 3. And I can do that by adding, or actually subtracting, 3 times row 2 from row 3 to get a new row 3. Subtraction of 3 times is the same as addition of minus 3 times the second row. So what I'll do here is I'll say the third row of A, so A sub 3 comma colon, that's the third row of A, equals, and now what do I want the third row of A to be? I want it to be done by the following calculation. Whatever the third row of A is right now, 3 comma colon, plus quantity minus 3 times A sub 2 comma colon. Okay, so we calculate the third row of A, whoops, and that should be a plus sign right there, not another equal sign. Typographical error, so let's correct that. Backspace, change that to a plus. Okay, so the third row of A is whatever the third row of A is right now, plus minus 3 times the second row of A. And so let's hit enter. And we now have this matrix. I think as far as we're going right now, this is far enough for us to easily solve the system of equations, which we will do very shortly. Let's talk about a row echelon form of a matrix. A matrix A is in row echelon form if it satisfies 2 conditions. First, every row that is entirely zeros lies below all the non-zero rows. if we look at this matrix down here, this bottom row is all zeros. The other rows above it in this case do have some non-zero elements. The second condition to be in row echelon form is if a row has a non-zero element, its first non-zero element is to the right of the first non-zero elements in the rows above it. Okay, so let's take a look at this matrix. In the first row, we have a non-zero element here. When we say first, we mean leftmost. So the leftmost non-zero element is here. If we go to the leftmost non-zero element in the second row, we would go down and to the right to here. If we go down to the third row and find the leftmost non-zero element, we go down and to the right, it's here. The next row, to get it, we go down and to the right again. And so this matrix is in row echelon form since it satisfies these two conditions. If we look at this fourth line and think of this as an augmented matrix for a system of equations, we can think of this this fourth line as being 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 equals 8. So 0 times this plus 0 times that plus 0 times that plus 0 times that equals 8. 0 plus 0 plus 0 plus 0 equals 8. There are no values of x1 through x of 4 that satisfy this equation, and that means that there are no values of x1 through x4 that simultaneously satisfy these 5 equations. Since there is no solution to the system of equations in this case, we would say that this system of equations is inconsistent. Inconsistent means has an empty solution set. Let's talk about consistent versus inconsistent systems of equations. Suppose we have an augmented matrix for a system of equations, and that matrix has a row of the following form. All of the elements in the row are zeros, except for the last element, which is a non-zero constant. In that case, the system of equations, as we saw before, has no solution. In that case, where it has no solution, we say that the system is inconsistent. On the other hand, consistent systems of equations are systems of equations that have at least one solution. So we need to find a way to determine whether a system is consistent or inconsistent. And what we'll do is transform the augmented matrix to row echelon form and then see if it has a row that consists of all of the elements being 0 except for the last element in that row. If we have a system of linear equations, algebraic equations, how many solutions can that system have if it is consistent? Well, we know that if the system of equations is consistent, then it has either exactly one solution or an infinite number of solutions. How do we determine which? So how can we determine the number of solutions to a system of equations by using an equivalent row echelon matrix, equivalent to the augmented matrix for that system of equations? Well, in order to answer that question, once we have the matrix in row echelon form, we'll talk about some variables in that equation being, in the system of equations, being leading variables or free variables. The leading variables are the variables corresponding to the leftmost non-zero entry in each row of the echelon matrix. The free variables will just be those variables that are not leading variables, the rest of them. So, how are we going to use these to determine how many solutions we have? Well, let's suppose that a system of linear equations is consistent, and if it has at least one free variable, it turns out that the system has an infinite number of solutions. And we can find all of the solutions by setting each variable equal to a distinct parameter, where each parameter can take any real number for a value. If there are no free variables, then the system of equation has exactly one solution. So let's look at an example concerning leading variables and free variables. Suppose we have matrix B, which is an augmented matrix for a system of equations, and it's in row echelon form. So in the first row, this 1 is the leading non-zero element, and so x sub 1 is a leading variable. Looking at the second row, we have a couple zeros and then a 3. This is the first or leftmost non-zero number in the second row, and it corresponds to the variable x sub 3. So x sub 3 is also a leading variable. Looking at the third row, going from left to right, the first non-zero entry we find is this one, and so another leading variable is x sub 4. So the leading variables are x sub 1, x sub 3, and x sub 4. These three variables corresponding to these three elements that are leading non-zero elements in each of those three rows. There's only one variable left that's not a leading variable, and that's x sub 2. So x sub 2 is going to be a free variable. As an example, let's find the solution set to this system of equations. 3x1 plus 3x sub 2 plus 2x sub 3 equals 4, and a couple more equations. First of all, let's write down the augmented matrix for that system of equations. The first row of this augmented matrix is going to be 1, 3, 2, 4. Just the coefficients of this side of the equation plus the constant on the other side. This second row comes from the second equation, 2, 6, 6, 12. The third row of the augmented matrix comes from the third row of the system, minus 1, minus 3, minus 2, minus 4. So the first thing we would like to do is to use the 1 up here, this leading 1 in the first row, to get zeros in the rest of the column below it. So first we'll do row 2 equals row 2 minus twice row 1. That's an elementary row operation. And when we do that, the second row is transformed to 0, 0, 2, and 4. The first and third rows remain what they were. Let's multiply the second row by a half. Row 2 equals a half row 2, which makes it 0, 0, 1, and 2. Now, next thing we'll do is, still using this 1 up here as a pivot element, we'll get a 0 right here. We'll use row 3 equals row 3 plus row 1, and that gives us the matrix with this first row unchanged, the second row unchanged. The third row, remarkably, is all zeros. 1 plus minus 1 is 0, 3 plus minus 3 is 0, 2 plus minus 2 is 0, 4 plus minus 4 is 0. So this row is 0, 0, 0, 0. And this is a matrix in row echelon form. Going from the top of the matrix to the bottom of the matrix, the leading non-zero entries go to the right, and any rows that are all zeros are at the bottom of the matrix below the non-zero rows. And so we look at this matrix, and because of this leftmost one in the first row, and in the second row this leftmost one, that tells us that x sub 1 and x sub 3 are leading variables. But then there's one variable left over, x sub 2, and so that's going to be a free variable. So to solve the system of equations, we'll let the free variable x sub 2 equal some parameter t. T can represent any real number. And then from the second equation, we have x sub 3 equals 2. That was easy to solve. And then we go up to the first equation and plug that in. So we start with x sub 1 plus 3x sub 2 plus 2x sub 3 equals 4. And we let x sub 2, a free variable, be t. We found out that the variable x sub 3 had to equal 2. So we arrive at the equation x sub 1 plus 3t plus 2 times 2 equals 4. x1 plus 3t plus 4 equals 4. So x1 plus 3t has to equal 0. So x1 has to equal minus 3t. So the solution set to the system of equations up here is the set of vectors x sub 1, x sub 2, x sub 3, such that x sub 1, x sub 2, x sub 3 is equal to the vector minus 3t, t2, where t can be any real number. So there are an infinite number of solutions to this system of equations. Let's make sure that we understand why this gives us an infinite number of solutions. What happens if I let t be 0 in this vector? In that case, we get the solution 0, 0, and 2, which we have here. Suppose we let t equal 1 in this vector. Then we'll get minus 3, 1, 2, which we have right here. Suppose I let t equal minus pi in this vector. Then we're going to get minus 3 pi, pi, and 2. So here's a third solution to that system of equations that we had. And we could continue forever coming up with more and more solutions to that system of equations. Any value of t plugged into this formula right here will give us a solution x sub 1, x sub 2, x sub 3 for that system of equations. So here's what we can comment on the use of free variables. If once you reduce the augmented matrix, there are free variables, how do we use them to find the solution set? Well, first we would set each distinct free variable equal to a distinct parameter, and this parameter represents an arbitrarily chosen number, and we would solve for the leading variables in terms of the constants in the equation and the parameters. Every choice of the parameter values results in a solution to the system of equations. Now let's discuss reduced row echelon form of matrices. If an augmented matrix is in row echelon form, we saw that we can back substitute, starting with the bottom equation and working up, to find the solution set to the system of equations. If we had free parameters, then we could have an infinite number of solutions. Well, it's even easier to solve the system of equations if the matrix is reduced to reduced row echelon form. We'll say that a matrix is in reduced row echelon form if it satisfies three properties. First of all, it's in row echelon form. That means that as you go from one row down to the next, the leading non-zero entry, the leftmost non-zero entry, goes down towards the right. Secondly, for every non-zero row, the leading non-zero row element, the leading row element is 1. And third, for every leading 1, all the elements in its column, the column with that leading element, above and below, are all zeros. Here is an example of a matrix in reduced row echelon form. If we look at this matrix, in the first row, the leading non-zero element in this row is right here, and it's a 1. Everything else in that column is zeros. Go to the second row, and we have the first or leftmost element being a 1. The leading element is 1. And everything else in this row are zeros. In the third row, we have a leading element of 1 here in the matrix. Everything else in its column is zeros. And then after that, we have 2 rows of zeros, no leading elements. So this matrix is in reduced row echelon form. Now, let's suppose we want to solve this system. Well, it's pretty easy to do. Looking at this matrix, the leading variables are x1, x sub 4, and x sub 5. So that means that x sub 2 and x sub 3 have to be free variables. So we just found that the leading variables are x1, x4, and x5, thus the free variables are x sub 2 and x sub 3. So for these free variables, I'll assign them parameters. Let's let x sub 2 equal s, and let x sub 3 equal t. So in that case, let's go to the first equation. We have x sub 1 plus 3x sub 2, but x sub 2 is s, plus 4x sub 3, but x sub 3 is t, plus 0 times x sub 4 plus 0 times x sub 5 equals 8. So that gives us x sub 1 plus 3s plus 4t equals 8. And we can solve this for x sub 1 in terms of these constants and these parameters. X sub 1 then is 8 minus 3s1 minus 4t. Now let's look at the second equation. It's 1 times x sub 4 equals 4. So we just get x sub 4 equals 4. Look at the third equation. 1 times x sub 5 equals minus 5. That gives us that x sub 5 is equal to minus 1. So what we have found right here is that x sub 1 is 8 minus 3s minus 4t, x sub 2 is s, x sub 3 is t, because these were the free variables, x sub 4 is 4, and x sub 5 is minus 1. And we can pick s and t to be any real numbers we want, and for each choice we will get a solution to the system of equations. To get a matrix in reduced row echelon form, we will use an algorithm called Gauss Jordan elimination. In this Gauss Jordan elimination, the first thing we do is use Gaussian elimination to transform the matrix to row echelon form. Then, secondly, for each row, let's multiply the row, if necessary, by a constant to make the pivot element equal to 1. So we do that for all the rows, make all the pivot elements equal to 1. The leading non-zero entry, the leftmost non-zero entry. Then we'll go through a process row by row. We'll start with the bottom row, at least the bottommost row that has a pivot element, and use the pivot element to get zeros above it. Now, we will see an example of this in a minute, But let's mention that on a TI-84 calculator, there is a built-in matrix function RREF for reduced row echelon form, and this will compute and display the reduced row echelon form of A. If you want to save this reduced form, say, back in the matrix A, you'll have to say A equals RREF of A. So you have to basically store it somewhere if you want to use it later. Here's a fact. Every matrix is row equivalent to one and only one reduced row echelon matrix. The reduced row echelon form of a matrix is unique. This is not true just for row echelon matrices. You might be able to start with a certain matrix, and by using a different sequence of elementary row operations, come up with different row echelon matrices. Both of the matrices in that case would be row equivalent to the original matrix. Row equivalent just means you're able to get from one to the other by using elementary row operations. And if we're talking about augmented matrices, it also tells us that the system of equations corresponding to the augmented matrix, in all of those forms, the row echelon forms, would have the same solution set. Using elementary row operations, remember, does not change the solution set to a system of equations when you alter it by elementary row operations. So let's look at an example of Gauss Jordan elimination. Let's start with the matrix B, given here, that is already in row echelon form. We have a leading 1 in this first row. We have a leading 3 in this second row, and we have a leading 1 in the third row. Okay, so let's see how we can get it in reduced row echelon form. So we start with this matrix, and we look at it, and it's in row echelon form, as we mentioned. And so let's start with this bottom row. Here's the pivot element, 1. I'm going to use this to get zeros in the rest of this column. So first of all, to get a 0 here, we'll do the new row 2 equals the old row 2 minus row 3. So 1 minus 1 is 0. 6 minus 8 is minus 2. Then after that, I would like to get a 0 up here instead of a 5. So to do that, I will use row 1 equals the old row 1 minus 5 times row 3. 5 minus 5 times 1 is 0, which we have right here. 10 minus 5 times 8 is 10 minus 40, which is minus 30. So now for this pivot element, we have zeros in the rest of that column. This is not quite in reduced row echelon form because this leading element in the second row is not a 1. So let's just say row 3 equals 1/3 the old row 3. And that makes this row up here equal to 0, 0, 1, 0 minus 2/3. Okay, and now we're not quite in reduced row echelon form yet, because in the second row our leading element is now 1 as we wanted, but the rest of the column is not all zeros. So what do I have to do to get a 0 up here? We'll do row 1 equals row 1 plus row 2. So 1 plus 0 is 1, 2 plus 0 is 2, minus 1 plus 1 is 0, 0 plus 0 is 0, minus 30 plus minus 2/3 is minus 32/3. And now this is the reduced row echelon form of this matrix B. For this leading 1, the rest of the column is zeros. In the second row, for this leading 1, the rest of the column is zeros. And for the third row, the leading element is 1, and the rest of the column is zeros. So we have used Gauss Jordan elimination to get this matrix into reduced row echelon form, and we started by going from the bottom up in this case, getting more zero terms in the rows. Let's continue with this example just a little bit further. Suppose that B is an augmented matrix for a system of linear equations in x1 through x4, and as we saw on the previous slide, the reduced row echelon form of B is this matrix. What is the solution set to this system of equations? Well, if we look at this, we saw that x sub 2 is a free variable because x sub 1, x sub 3, and x sub 4 were leading variables. So we'll set x sub 2 equal to, let's say, s. So this first equation then is 1 times x sub 1 plus 2 times s equals minus 32 thirds. So that gives us that x sub 1 is minus 32 thirds minus 2s. Looking at the second equation, it's 1 times x sub 3 equals minus 2 thirds. So that just tells us that x sub 3 is minus 2 thirds. Looking at the last equation, it tells us that 1 times x sub 4 is 8. So x sub 4 is equal to 8. The free variable, remember, was 2. And we set x sub 2 equal to the parameter s. And so that completes this 4-element column vector. X sub 1, x sub 2, x sub 3, x sub 4, this vector has to equal this vector. And for any choice of s that you use, this will be a solution to the system of equations that we started with. Let's go back to the initial value problem that we saw near the beginning of this lecture. The initial value problem had a fourth order ordinary differential equation and initial conditions. The augmented matrix that we got for the system of equations where the unknown quantities were c sub 1, c sub 2, c sub 3, and c sub 4 was given by this matrix here. C1 plus C sub 3 equals 7. Second equation, minus 3C1 plus C2 plus 2C3 plus C4 equals 9, and so on. Looking at this first row, that corresponded to 1C1 plus 1C3 equals 7. And we called this the matrix B in Sage Math. B equals matrix, and then we have a parentheses here and a parentheses here. Inside those parentheses is the definition of our matrix. Here is a square bracket, which you can think of as representing this bracket here. And over here we have another square bracket, which we can think of this as being this bracket here. Now inside those two square brackets, we have the rows. The first row, square bracket 10107, is right here. We had show B so that we could see it finally. Here's the second row, here's the third row, here's the fourth row, and we get this matrix corresponding to all four equations in the four unknowns C1 through C4. We can calculate the reduced row echelon form of this matrix B, and then we can display it. And when we execute that command, here's what we get. This first row corresponds to 1C1 plus 0C2 plus 0C3 plus 0C4 equals minus 12 over 125. So basically, C sub 1 equals minus 12 over 125. Looking at this matrix here, we can see what C sub 1, C sub 2, C sub 3, and C sub 4 have to be in order for all of the initial conditions to be satisfied. C sub 1 was this number, C sub 2 was this number, C sub 3 was this number, and C sub 4 is this number. So just plugging them in for these C's, we get the solution to the initial value problem is this. When we execute these two lines of code, each of them executes, I would say, in much less than 1 second. So using something like SageMath or perhaps MATLAB or Octave or Mathematica or Maple, all of those have similar commands for handling matrices. SageMath is nice in that it does exact calculations here rather than decimal approximations. Let's talk about a homogeneous system of linear equations. In a homogeneous system of linear equations, like the one down here, the right-hand side constants are all zeros, as we can see here. If we have some of these constants not being zero, then we would have what's called a non-homogeneous system. So some systems are homogeneous, some other systems could be non-homogeneous. Now, what's nice about homogeneous systems? What are a couple important facts that we should know? Well, first, a homogeneous linear system always has at least one solution, which is called the trivial solution. If I let all the variables x sub 1, x sub 2 through x sub n all be 0, then all of these equations would be satisfied because this constant times 0 plus this constant times 0 plus all the way through this constant times 0 does equal 0. And similarly, all of these other equations would also be satisfied. So homogeneous systems like this always have a trivial solution. And since the solution set is not empty, that tells us that homogeneous linear systems are never inconsistent. Another fact that we should know is that if a homogeneous system has more variables than equations, then there must be a free variable, at least one free variable, and thus the system will have an infinite number of solutions. As an example, what can we immediately say about the solution set to this system of equations? X sub 1 plus 3x sub 2 plus 2x sub 3 equals 0. 2x sub 1 plus 6x sub 2 plus 6x sub 3 equals 0. Well, first of all, we notice that on the right-hand sides, the constants are zeros. So that tells us that what we have is a homogeneous system of linear equations, and thus we know that it is consistent. It does have at least one solution. The other thing we notice is that we have two equations here, but the number of variables is 1, 2, 3. We have 3 variables, but only 2 equations. Thus, that tells us that there has to be a free variable. We don't know which one, but it doesn't matter. And thus, this system must have an infinite number of solutions. So here are the main points of this lesson. A system of linear equations can have 0, exactly 1, or infinitely many solutions. A homogeneous system, however, always has at least one solution. We can represent a system of linear equations by an augmented matrix. We can use elementary row operations to transform a matrix into another row equivalent matrix by using either Gaussian elimination or Gauss Jordan elimination. And once we have this matrix in row echelon form or reduced row echelon form, we can identify the leading variables and the free variables and can use that information to find the solution set to a given system of linear equations. I hope you enjoyed this lesson, and please continue with the following lessons to come. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.